So my job here, and this is something that you need to absolutely understand. We need the language of atoms. And the only way you can do this here is that we got to talk about atomic structure. We need you to be an expert at atomic structure and the periodic table. And my experience with Physics 10 is that people are just going to knock this out of the park. But it's the details of what's going on that people typically have the most problem. So what we want to go do here is that, once again, when I talk about the periodic table, my favorite online periodic table is what they call P table. And what I like about it, it's a dynamic periodic table. That means you can click the cells and highlight and just focus on one. So that's what I'm going to keep using. So if you did a search for P table, that's the table that you would get. And I also linked it in the lecture notes so you could see where it's at. Okay, so what is my job here? So our job is to get you to know, one, the number of protons and neutrons in the nucleus. That number is what's known as the atomic mass number. And if you look at standard notation, that's what they call A. The next thing that we need here is that we need the number of electrons and electron shells. And sometimes people call these orbitals, but that's really the language of Rutherford talking about here because of his planetary model. And then Bohr continued to use that language. And then what we need to know here is we need to figure out from the number of neutrons, and then we're going to look at nuclear isotopes. And the isotopes then tells us really about the atomic mass number and why it's not a perfect number. So let's keep going. So the first thing I need to do here is that I'm going to talk about atomic mass. So what you're going to see here is that I've made clips before you got here of the periodic table of particular cells. So they don't pop out of, empty space. They come from that periodic table, the P table. So here we go. So the first one that we want to talk about is that we want to talk about atomic mass number. So what's the origin of the atomic mass? Here's what we know. The atom is made of two parts, right? One, we know about the nucleus, and inside the nucleus, it's protons and neutrons. And then, of course, we have the electrons. So here's what we know. Protons and neutrons have almost the same mass. It turns out that the neutron is a little bit heavier than the proton. So what this means here is that I want to start writing some notation here. So that means that the mass of the neutron is equal to the mass of the proton. So a couple of language things. So from now on, if I see a neutron, I'm going to draw it in blue. And this guy is a neutron. And a lot of the times you'll see me write it as N naught. And when I draw a proton, I'm going to draw it in red. And I'll call, of course, we'll call this a proton. And the language that I use for proton, you'll see I'll draw it as P plus. And the reason why it's N naught and P plus is because it tells us about the electric charge of these guys. So what we know here is that the nucleus is a tiny, extremely dense region where protons and neutrons bind together. So this is a bad picture of the nucleus. So when I think about a nucleus here, remember, bad model. So what we find here is that we have a series of collections of protons, and then we have dispersed within them a number of neutrons. So that's the picture that people typically say is a nucleus. Just like the planetary model is a bad model, this is a bad model for the nucleus here. But for right now, all we know is that we got a tiny dense region where these protons and neutrons bind together. Okay, so now we've dealt with the mass of the neutron and the proton. So let's keep going. So now what I'm going to look at is I'm going to look at the next thing. The mass of electrons is extremely tiny compared to the neutron / proton. So remember, is that so because we're going to start talking about the electron, here's what I'm going to do here. So I'm going to say that the mass of the neutron, right, is equal to the mass of the proton. And this is equal to 1,800 masses of the electron. So that number is quite significant. Now let's talk about the electron. So if I look at the mass of the electron, right? So when I look at the electron, what am I going to do? Well, this one I'm going to draw in green. So if you see a green, we know that that's the electron. And a lot of the times I get lazy. So the way we write electrons is we write an E with the minus sign. And that tells us that it's an electron. Now, let's look at the mass of the electron. So as an analogy, to get you to see, imagine that you have a balance, sort of like a teeter-totter. So what does this mean here? So if I have a balance like this, and what we want to do here, if I try to balance the masses of this situation, what do I find here? I find that if I take one proton, right? One proton, remember they're in red. And if I look at the electrons, I have to stack how many electrons? A huge pile of electrons. How many electrons do I have to add? 1,800 electrons. So 1,800 electrons is what balances out one proton mass. So here's my analogy here. So my analogy here is that you could imagine that I have a bowling ball. And so when I'm thinking about this bowling ball, we all know that a bowling ball could be quite heavy. So if I have a bowling ball, the equivalent of an electron mass would then to compare the mass of the bowling ball to a mass of a marble. So if I look at this, that's a good comparison. So if I compare the mass of a marble to a bowling ball, of course we're going to ignore the mass of the marble because it's so tiny. That being the case here, check it out. The total mass of the atom is then going to be what? The mass of the atom. And we could see here that I'm going to have the mass of the neutrons plus the mass of the protons, that's the nucleus, plus the mass of the electrons. So since we're comparing bowling balls to marbles, we can clearly come in here and just ignore the mass of the electrons. So when I look at this thing, you could see that most of the mass is inside the nucleus. So here we go. So when we look at the atomic mass, it's the neutrons and protons. So now, here we go. Definition, the atomic mass number is what we call A, and this is the mass of the protons plus the mass of all of the neutrons. And what does this tell us here? This tells us how many protons and neutrons are in the nucleus. And since they do that, a lot of the times you'll see me say, yep, how much is in that thing right there? So what we find here is that this is what the atomic mass is right here. Okay, the atomic mass number tells us how many there is. So let's go look at some examples so you can see what I'm talking about. So So if I look at this, let's go, I'm going to show you what I did here. So I'm going to go to the periodic table. And here's the periodic table. And what I'm going to do here, what you're seeing here is that there's the periodic table. So what I'm going to do now is that I'm going to do this here. I'm going to come in and I'm going to get calcium. How do I get calcium? All I do is that I come here and I click on that. Now I got calcium. So then I'm going to take an image of that square. And that's how I'm going to get all of these elements that you see here. Okay. So here I go. So I went in and I got a square of calcium. And I got another one. So I went in and I picked a second element, one of my favorite atoms, iron. By the way, I have many favorite atoms. There's so much cool stuff about atoms. Okay, so here we go. So what you're seeing here is that this guy is calcium. It's not the way you spell calcium. And this atom, as you can see here, is that this is iron. So what am I focusing on? This number here are the atomic masses right here. So we got to be careful here. So these are weighted atomic mass number. So these are the atomic masses right here. So what we do here is that we round to the nearest integer. So what do I mean by that? So when you look at calcium, you can see that it's closer to 40 than it is to 41. So then when I look at its atomic mass for calcium, that number is 40. So that means that there are 40 protons and neutrons inside calcium's nucleus. So when I look at iron, it's closer to 56 than it is to 55. So then when I round here, I then say, okay, the atomic mass for this guy is 56. So that means that I have what? 56 protons and neutrons inside that nucleus. That's what I mean by the atomic mass.